Hi, my name is Mr. Group, and we are going to be talking about causality. Causality is the science of cause and effect, and we are not going to be making any assumptions more than what a layman can understand. So, this is going to be a very casual introduction to causality. Yep, that's me. I'm evil as anyone can get. Now, when we talk of causality, there is a dependence of cause and effect between two variables. Since as a human being we talk about two things, dependence between two things. In mathematics and sciences we talk about interdependence of cause and effect between two variables that you are measuring. You're not saying that football is dependent on the leg. You are saying the location of the football in terms of x, y, and z positions is dependent on the angle of the leg in degrees, like that. So correlation can indicate causal relationships. A person who is very heavy smoker, which is the variable X, has a higher risk of suffering from lung cancer, variable Y. So correlation does not itself prove causality. Correlation is that these variables affect each other, but they may or may not be causing each other. So two variables can have a statistical relationship without there actually being any mutual influence. There are so many things in the world which seem to be, moving together upwards or downwards, and but they are not causing each other. These things are called spurious correlations. If you keep everything constant in the world, and if you change X, if it results in Y, then it causes Y. But if you change Y, it does not necessarily change X. That is how we check for causation. Now, back to correlation. Correlation is used in common language to denote some form of association. We say that there is a correlation between fog and the attacks of wheeziness. We feel that if you have a condition and there is a fog, there is some correlation. You get your condition gets aggravated in fog. But instead of talking about things in statistical terms, we talk of correlation in terms of two quantitative variables, like I was explaining in the previous slide. And for correlation to be measured, we assume that such associations are linear, where if you increase or decrease one variable by a fixed amount, there is a increase or decrease in the other variable. The degree of association, which is measured by correlation coefficient, is denoted by R. It is also called the Pearson's correlation coefficient after its originator, and is a measure of linear association. If you need more complicated forms of correlation relationships in terms of polynomials, etc., there are other complicated measures. This is how correlation is measured on a scale of +1 through 0 to -1. A full correlation between two variables is expressed as either +1 or -1, which basically means that when one variable increases, the other increases, then the correlation is positive. If one decreases as the other increases, the correlation is negative, and complete absence of correlation is represented by 0. Now, there are these things called counterfactuals which we have to consider in our arguments. If somebody says that A causes B, then he has to think about if A causes B and if A did not occur, then B would not occur. What would have happened if I had taken a different course of action? Would the children still have taken drugs if dad had spent more time with the teenagers? I mean, thinking of things like if I had left the event early, I would not have met my soulmate. These are all counterfactual arguments. Now, you must have heard of the phrase correlation does not imply causation. This refers to the inability of legitimately deducing a cause and effect relationship between two events or variables solely on the basis of a observed association or a correlation between them. Just because is increasing and shaved heads are also increasing does not mean shaving your head is causing the sales to go up, which means that correlation does not imply causation. This is a spurious correlation. If you measure the, thousands of variables in the economy and society, US spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. Does not mean that if people commit suicides, US increases its spending on space, science, and technology. Number of people who drowned by falling into the pool and films Nicolas Cage appeared in does not mean that if Nicolas Cage appears in more films, more people drown by falling into the pool. Per capita cheese consumption and the number of people who died by becoming tangled in their bed sheets. I mean, cheese has nothing to do with people dying in their due to their bed sheets. Now, Simpson's paradox says that the same data can give contradictory conclusions depending on how you look at it. If you look at the diagram on the left, as you increase treatment, the risk of heart disease increases, which is counterintuitive, right? As you increase treatment, the rate of heart disease is increasing if you plot this line like this. But if you divide this data into by gender into male and female, as you increase treatment, the rate of heart disease actually decreases. So the same data gives contradictory conclusions depending on how you look at it. There is also a problem of symmetry. If this is the equation between symptoms and diseases, okay, and we say that disease leads to symptoms, we can invert the equation. But can we then say that symptoms lead to diseases? The problem, the reason this problem arises is because correlation is identical and equal in both directions. And with correlation, you can invert the equation, and it feels that since the correlation will remain intact, it feels that the inverse causality is also true, but which is not true. The process of causal discovery aims to uncover causal structure from observed data. In other words, given a data set, we need to design a causal model that describes it. So a causal model will be like a graph of things depending on each other, etc., and causing each other. So at its core, causal discovery is basically an inverse problem. I mean, if you look at the water that is spilled on the floor, you have to predict the shape of the ice, which caused that, the melted water to flood the floor. Although this sounds impossible, the basic strategy is to narrow down all possible solutions with assumptions. It is an intellectual discipline that considers the assumptions, studies the designs and estimation strategies that allow researchers to draw causal conclusions based on data. It is a complicated science. But for example, what is the average treatment effect of intervention? What is the effect of a treatment on customer spend, engagement, retention, and so on? Will providing a treatment in this scenario work? Can we fix this situation? Why did a treatment work? And in the case of multi treatments, which treatment or which investment should we recommend to customers? Confounders. Confounders are like catalysts. Alcohol use can lead to lung cancer, but if you are also smoking, which is a confounder, it catalyzes and amplifies the effect, cause and effect relationship by more than 10%. So, in the presence of a confounder, the cause and effect relationship between alcohol and lung increases by more than 10%. That is the definition of a confounder. Instrument variables are variables that are highly correlated with the treatment. I mean, it feels like, they'll be causing the outcome. along with the treatment, but they have no impact on the outcome. They are arranged like this. Instrument variable affects is correlated with treatment. There are confounding variables, and then there is an outcome. Causal inference is basically is fundamentally based on a couple of things like potential, actual, and counterfactual outcomes, confounders, selection bias, and instrument variables. The mathematics of causality is based on is described by two things. Uh, these are structured causal models, and they are of two types: a directed acyclic graph and a structured equation model. Now, if you see this, a directed acyclic graph represents a causal structure by showing who listens to who, or who basically who gets caused by what gets caused by what, and more importantly, what does not get affected by something. Okay. Structured equation models basically represent relationships between variables. These equations have two peculiarities. First, they are unidirectional. The function will result in the outcome, and they cannot be inverted. Second, the equations can be non-parametric, which means that the functional form of the equations is not known. They could be polynomial, they could be exponential, logarithmic, or whatever. Now, which is better? Are directed acyclic graphs better, or structured equation models better? Now, directed acyclic graphs do not have cycles, and they have a direction. And structured equation models are a great mathematical representations of functions that act on treatment variables and result in outcomes. On the face of it, we might feel that once we have these equations, why do we need the visual representation of the graph? But the equations can be very complicated to understand and get a feel of the underlying cause causal dynamics. So a visual representation like directed acyclic graphs are very useful. Especially they have been used in some methods of evaluating causal effects. What is the do operator? Suppose Z causes X and X causes Y. If you isolate X from the rest of the world and just change X so as to impact Y, this is an intervention. This is what a do operator does. It is a way of manipulating uh, variables so as to figure out the cause and effect relationships. The do operator and the do calculus was developed by Julia Pearl in 1995 to facilitate the identification of causal effects in non-parametric models. Now, it has a lot of rules, and you can see these rules. A do calculus allows you to insert, delete observations, exchange actions and observations, and insert, delete actions. Besides the do calculus, there are methods in machine learning which allow you to figure out causality. Now, remember this diagram. There are instruments, there is treatment, there are confounders, and there are outcomes. Now, in the double machine learning mechanism scheme of things, what we do is we predict the outcome from a set of control variables, and we also predict the treatment from a set of control variables, and we combine these two. We can use any machine learning model to do both the parts, as long as they have a certain set of statistical properties. This is the book of Why by Julia Pearl. This is like the gold standard in the science of causality. The final frontiers of AI are basically three things: maths, logic, and causality. If machines can understand math, logic, and causality, besides doing all the wonderful things that they are already helping us do, we would have achieved AI. I told you I was evil, didn't I?